Hi, everyone. Thank you to all the organizers for inviting me. I'm kind of an interloper. I'm not someone who went to Cambridge, but I'm really enjoying my time here this week at this broad meeting. And thanks to you for coming back from the break. It seemed like it was a little bit of a battle. Anyway, so as you can guess from my slide, I'm going to be talking about what we can learn in the science of direct imaging of supermassive black holes using a technique called global very long baseline interferometry, or VLBI. And in particular, I'm going to be talking about the particular brand, which is using the millimeter band called the Event Horizon Telescope. Other brands are available, but we will not be talking about those in this talk. My particular twist on this is to talk a little bit about what we stand to learn, and in fact, I think we need to learn by combining images like this with multi-messenger signals. And what I mean by that is multi-wavelength data. That's mostly what I'll touch on in this short talk. But of course, you can think that this is also important for things like neutrinos, cosmic rays, and eventually signals like excuse me, gravitational wave. So I know this is a very busy audience with lots of different fields, so I plan to just kind of give a broad as possible overview of some of our recent and maybe hint at the upcoming results, and give some perspective on what's coming down the line, because as maybe some of you are not aware of, we're really just at the beginning of our studies. These images are just the start. They're not the end of the story, though they were a big groundbreaking moment for us. And the Event Horizon Telescope and related projects are basically being built out into what we call loosely this next generation projects on NG-EHT. So I'm just going to mention as well that these are large collaborations. So when I show these results, I'm representing the work of hundreds of people, including many young people. But I'll try to squeak in a couple results from junior scientists in my own group. And let's see if I can get the hang of this pointer that I show in orange always and sometimes with pictures. OK, so just to set the stage so everyone's on the same page, let's start with some big picture questions. And these are, the burning questions that we have that might drive people like us to try to build a planet-sized telescope. And, this image of SIG-A, it's a supermassive black hole emitting these very large jets here. And this is a great example of a myriad of types of objects in the universe that are basically driven by gravitational accretion. And so they can be bigger than this, they can be smaller than this, they can be transient, and they can be steady, but they're all sharing some similar physics. And at the end of the day, we'd really like to understand this universal mechanism. And so there's a wide variety of questions for black holes in particular that I'm not going to get into detail, but I'll try to touch on in this talk. But the punchline is basically that we really want to know what comes out as a function of what goes in. And not into the black hole, but of course, like threading into, some of it going in and feeding the black hole and growing it. But also, we're mostly interested in trying to understand this accretion physics and these processes that lead to basically, down near the event horizon. Wow, this is really hard to use. OK. I'm trying to aim it down near the event horizon to these extremely large scales. They can be billions of times bigger. And so the energy that's being sourced down here has to be carried out. And we'd like to understand all the processes along the way, but also how to calibrate these effects. And the idea is that if we can calibrate and understand this by getting down information both near the event horizon as well as at the largest scales, then we can start to apply this to this myriad of other objects. And so that kind of sets the stage for how we came to the idea of building this array. And I know some of you have heard me talk about this in SHEP, but I'll go through this for everybody else. So the Event Horizon Telescope project is not something that we built ourselves. We're basically borrowing time on other facilities. And the reason that we went for the millimeter, if you think about lambda over d, we knew that we wanted to see the innermost regions of several nearby black holes, and so we needed at least a resolution of about 20 microarc seconds. So if you do the calculation, limited by the size of the Earth, you find out that you have to be somewhere up as high as possible for this technique, which hadn't really been done before at this high wavelength. And that was where a lot of the difficulties and the time and the developing of all these new algorithms and so on came in. So just to say quickly about how this works, we basically, the array gets put into this mode for some period of time, about a couple weeks during the year. In fact, we use ALMA in a mode which is also phased together, which we're competing with some of you probably for this time. And then we are given typically about 6 or 7 days and nights during a 2-week period to trigger these results. It's very complicated in terms of trying to manage all the multi-wavelength we also try to do. the array has been growing significantly since the time that we've published our first results. So we had 8 facilities in 2017, and then we added the Greenland telescope at the top here in 2018. So 2017 was 8 facilities. Then we had a couple gap years due to things like pandemics. 2021 and 23, we added another single dish, as well as a full array, the Noema array, which really increased our sensitivity. And then in the last year, we actually have been testing facilities in Asia. So we want to have as much of the Earth covered because we're using this technique that takes data while the Earth is turning, and that changes the projection of the baseline. So the more baselines, the better. We're also starting to test, as of this year, another frequency. So we've mostly been operating in our sort of main frequency is 230 gigahertz, but we've started to test 345 gigahertz. And of course, with lambda over d, that means that gives us slightly better resolution, maybe even more, something like 15 microarcseconds. So to give you some sense of this parameter space, we use this horrible plots, if you're not familiar with it, called the UV plane. We're basically taking a Fourier sampling of the image on the sky. And so we make this plane to represent the sizes of the baselines. And so what you can get from this is that the smallest baselines are probing the largest scales. And so for M87, this is basically telling you about things like the large-scale jets. And these very, very large baselines are the ones that we use to start to probe the regions near the black hole. And the black, if you can kind of see the difference in here, was what we had in 2017, and then everything else you see was added since. So you can see that the array, and the more squiggles you have, the better, because you're filling in, if you had a perfect one dish the size of the Earth, it would just be completely full. So this tells you about your sensitivity. So you get better sensitivity with more squiggles, but then also the fact that you have more squiggles spread out around here gives you more dynamic range. So increasing the baselines and having more sites is something that we really want to do. And now you can also see that for Sag-A-Star, the difference isn't quite that big, and that's because the new facilities we added are in the north, which are not as important for observing something in the southern hemisphere. Okay, so where are we now at the moment? And you've probably seen these images before, but the state of the art at the moment is that we've published most of our data from 2017. We have a couple, we're also looking at several supermassive black holes where we can't see the event horizon, but we see the inner parts of the jet, so we do AGN studies, and I won't talk too much about that in this talk. But we've got the full polarization data out now, and you can see that in these images. So we have information about the magnetic field structures very close to the black hole as well. And the question is now, what do we start to learn from this? The other thing I want to mention is that this might seem kind of slow, that we're in 2024 and we're just starting to publish 2018 and moving forward. And the reason is that this was entirely new, as I mentioned, and there was just an enormous amount of work. We now are in a situation where we've really kind of got our pipelines and our analysis tools a little bit more standardized. We've run many, many more models, and so we're really going into full production mode. And I think you're going to start to see a lot more results coming out, one on top of the other, finally. So it's kind of an exciting time. And unfortunately, I can't tell you about everything, but I can hint a little bit about what's coming. So what have we learned from these images? And I would say the first thing we learned is people like memes. We were not really expecting this when we did the press conference, but it was all over the internet. And that was our first sense that this actually resonated with people besides a bunch of nerdy scientists like us. But in all seriousness, these images are kind of unimpressive astrophysically, but what's inside of them is very impressive because you're looking at this convolution of astrophysics and gravitational effects. And so we made this little movie here, and what you can see is that we like to sort of break up the photon paths to explain things. So photons that are really just not really bent by the black hole or maybe distorted a little bit, but coming more or less straight to you, contain all the information about the astrophysics, the geometry, the particle physics that we'd like to know. But as soon as the photons start doing a U-turn or more, or many more around the black hole, they get focused to this thing called the photon ring, which is the part of the image that actually gives you information about the space-time metric. And so, if you believe in general relativity, then the idea is that this ring should be on the order of about 5 times the size of the event horizon. It's gravitationally lensed, so it's magnified a little bit, plus or minus around 4%. This was all calculated going back to the 60s and 70s, so it's quite well understood. But if you have your favorite model, you can look for deviations in principle from general relativity as well. The problem is that it's not easy to pick these two parts of the image apart at the moment. So one of our main results is that we're able to constrain general relativity to about 10% for Sagittarius Star to 20% for M87. And that doesn't sound super impressive. The reason that we're stuck a bit is partly that we don't see an image this beautiful. We're stuck with this sparse sampling, so it's very fuzzy. But the biggest contributor to our errors is actually our theoretical models, because what we need to do is model black holes, model all the radiation, and then forward fold, and then do all sorts of comparisons to try to figure out which model is the most, the best explanation of a particular image. And of course, if you think about something that's dynamically changing, and I'll come back to this, and you just have one snapshot, that's actually quite difficult. So one of the big questions is, how can we start to do better than this? And to give you an idea of the degeneracy, and this is all in our collaboration papers if you're curious, but what we do is we explore parameter space of things like the GR parameters, like black hole spin. In some of our later papers, we go away from GR and test things like wormholes and boson stars if you're interested. But for the main workhorse papers, we mostly stick to assuming general relativity is correct and then trying to see how well we do. And what happens is that you end up with different models. So you can have like weak magnetic fields and strong magnetic fields. You can have different spins, different black hole sizes. And then there's this R parameter. And I'm not going to go into the details of this, but basically this kind of relates to what Christoph was talking about this morning, that we don't have the particles in these fluid models that we're using to model the plasma near the black hole. And so what we have to do is essentially a subgrid model. And what the most common one that we use is a very simple one where we energize the light emitting particles, which are not in our single particle simulation, but as a function of the magnetization. And so basically, depending on whether it's in the jet or the disk, depending on how you turn these knobs, you get some different images. And the problem is that we end up with many things that look the same, at least for M87. And that was our original results. And what I want to start to move into now is giving an example of how we can start to break this degeneracy using things like multi-wavelength and other types of information that we have. And that's really the important direction at the moment. So one of the key other results besides our constraints on GR that came out of all the modeling we've done of these images so far is that it's very peculiar. These are two completely different black hole states. M87 is sort of middling in accretion, but it's basically in this radio mode, you would call, like of giving feedback. Whereas Sagittarius A star, as far as we can tell, this is an image with ALMA, and we don't really see any sign of a large jet at the moment. Yet the models that we have prefer very strong magnetic fields in the configuration that in our simulations produce jets for both of them. So one of the big questions we now have is there something missing in our simulations? Are we getting something wrong? Is there another variable? Or is there maybe some kind of jet and a reason that we're not seeing it in this really complicated region in the galactic center? Because it is an extremely weak black hole. It's one of the weakest ones we know of. And so maybe the jet's just kind of hiding in all that mess. And so one of the ways we're trying to look at this is also to probe the model space a little bit with also some of these other signals. And so for every campaign, even though we haven't even started really touching the surface of these data sets, we were very prescient in that we started to arrange broad multi-wavelength campaigns for almost every source that we look at. And so this is the one from 2017. So at the moment we were taking this image, we were also taking all these images and getting data from the radio all the way up to the X-rays and to the gamma rays even. And this is becoming important because you can't really produce high energy emission like X-rays and especially gamma rays without breaking your fluid model. You have to accelerate particles, you have to make cosmic rays. And so this is where a lot of the theory work has to be improved so that we can start to actually approach these data sets. So I'm going to start by giving you a sense of first with Sag star, how we use, in the most recent papers, how we actually use the multi-wavelength. Now, Sag star doesn't have these big jets, but it's flickering. The black hole itself, or the region right outside the black hole, seem to be flickering on a very fast basis all the time. Sometimes there are bright flares. So when we do these multi-wavelength campaigns, we actually hope to catch the bright flares. And what I can tell you, but not show you, is that we did actually capture flares in several of our data sets. And oh my gosh, I got to really speed up. So anyway, so basically we have, we know that there's motions associated with the flaring, and we're starting to be able to see some of this information. Here's just to show something about our multi-wavelength data set. But basically, we start out now with hundreds of models, and by incorporating these data sets, we can actually start to rule out many of these models by putting the images together with the multi-wavelength. And we end up getting down to 2 models. And these 2 models are the ones for Sagittarius A star that also are very similar to the models that we prefer for M87 with the strong magnetic fields. Now, if we include the new polarization data, these are these horrible sort of pie charts that we use for pass-fail models, but you can see green means good up here, blue means good down here. The polarization picks out only one of these models at the moment. Now, does this mean that we're gonna, bet our lives on this model? Maybe not, because there's a lot of things that are missing, but it's very interesting, and it shows the power of using all this combined signals to start to reduce our errors, and that in turn would help our abilities to test things like general relativity, but particle acceleration as well. Now, the variability is a big problem. None of our models are actually quiet enough for Sagittarius A star. They're all too variable. And I'll come back to this, but this also is something that may have to do with our treatment of these kind of subgrid particles in our modeling techniques. So just to flash a little bit of work of what I would say some of our horizons coming up and what you could expect to see. One would be that we're increasingly combining the images with information from the full SED as much as possible. And this is work from 2 of my PhD students, Wanga and Ritik. And you can see here's a movie showing a simulation, and then this is the SED coming out from M87 against the data. We're not even showing the gamma rays, but here are the X-rays. And when you can see that we're way below the line. And this has to do with the fact that it's very, very difficult to excite particles in a self-consistent way. And we're really struggling with this. So that's where a lot of the work is going to come. But you'll start to see this as an increasing constraint in the coming years. Now, another big horizon is going to be dynamical movies. So one of the things when you look at these snapshots is you remember we're taking these over a period, sometimes multiple times, multiple nights over like a week. For Sagittarius A star, which is changing on timescales of minutes, or seconds or minutes, we're basically not able to collect enough data to see any of this dynamical motion. So we're integrating all of this, and that can also maybe skew some of our results. But our array at the moment is not good enough to have the sensitivity to break the observation into parts. So by improving the array, especially on the eastern part, that's some way that we can start to actually get motions as well. Now, M87 is actually moving in this image, but you can hardly see it. It's actually quite slow, so a snapshot really is a snapshot, but then the problem is that if we look once a year, it's going to take us forever to get an actual movie. And so the first frame in our movie has come out in 2018, and you can see that the ring has shifted. And this is interesting because it's far enough apart. These are basically 2 random draws. So you can start to look at even, just taking 2 random draws of your simulations, and it already is a little bit constraining. And this is actually work my bachelor student just finished. But these are probability distributions of seeing the ring moving certain angles from a reference angle. But you could basically see there's a strong peak, but these strongly magnetized models have a much broader distribution, which means it's easier to pick 2 random picks and get 30-degree swing than from the weaker magnetic field models. And that's a result that many different groups are finding. So this is also one reason why we're pushed toward these more turbulent magnetized models for this. But of course, what we really want is to have many, many more snapshots of this. And another interesting fact is that the jet of M87, where our EHT image is down here somewhere, is wobbling on a similar time scale. So the question is this related to the precession of the jet, and is some of the light coming from the jet, or is this actually something else going on? So this is something we will find out over the years of observations, and there are plans afoot, we hope, for a movie campaign in 2026. Another new horizon is that we found the first gamma ray flare since 2010 in our campaign. And this is it's on archive at the moment. We had to put it on archive because we needed to get more multi-wavelength observations through the tags. So you can look at this, but it's pretty exciting, and we see some hints of hardening. And this is the beginning of an era where it argues for more monitoring together with high energy to start looking at these problems of, for instance, the source of ultra-high energy cosmic rays. There's a big debate that's been in the field for decades about whether cosmic rays are being coming from the outer jets or from the magnetosphere of the black hole. And by imaging at the same time in these flares, we hope we can start over time to sort this out. Another horizon is this improvement of the particle physics. And these are the last 2. I'm going to talk about this one and M87 in general. But what we're trying to do is improve the subgrid treatment of these particles. I won't go into a lot of detail about this, but just to give you a sense, this is work by my PhD student, Leon. But this is the RMS variability taken in random 3-hour chunks, and the gray here is the historical data. And all these other curves are basically showing you simulation sets. The original sets from our EHT original simulation set was way high. That's what we call the variability crisis. And then what Leon has been doing is increasingly looking at different kinds of physical methods that look at how the particles get heated, and it's bringing the curves closer. So we haven't solved this problem yet, but we think this may be an artifact of some of the microphysics that isn't well treated. And I think just like the cosmology community, we struggle with getting the small scale physics that is orders of magnitude smaller. You know, we can't capture this, how to do this properly. And so coming almost to the end of these quick highlights, many of the jets we're seeing, both with the Event Horizon Telescope, this is Centaurus A, but these are other sources that are seen with other VLBI networks, are hollow. They're lit up on the sides. This is very hard for our models, actually, at the moment. It tells us that a lot of the dissipation is probably happening preferentially on the sides of these jets. And so some work of my student, Shubrat, we're doing, this is looking at the inner part of a simulation with sort of the disk and the jet boundary. This is just the zoom out of this. But we're starting to get to the point, the black lines are magnetic fields, where we can do very high resolution, put AMR along the sheaths, and eventually start to do local box type simulations. A little bit technical, but for those who are interested, we're hoping to get to the point where we can start to compare and even move down and do some work with particle and cell treatments. And this is actually doing tracer particles, and we're looking to start to put in particles in the way that Christoph was mentioning, but for black holes to do things like diffusion coefficients and acceleration. So there's a lot that's happening on a very small scale compared to cosmology, but quite related. So this is what's to come. This is data we already have in the bag. So you can see basically, and we haven't even put 2024 here, but these are all the sources. Red means we haven't started, but black are ones that we've published or we're working on. And this is everything we have besides EHT. So there's an enormous data set that's going to be of use for many, many years to come. And then as we start to expand the array, so this next generation expansion phase is starting. Different countries around the world are sort of looking at contributing to the array. And the yellow is what we had before. Then we added Noema. And now you start to see these pink and white ones. The one that I'm involved in is called the Africa Millimeter Telescope. It's funded in part by an ERC synergy grant that I have together with Heino Falco and Rob Fender. We're partnering together with the University of Namibia. You might recognize Hiko here. This is Lot, the first ever PhD student in astronomy in Namibia. Hiko is the second. And you might have seen some students from Namibia here at this meeting. They are involved in doing outreach as part of our project with the AMT Mobile Planetarium. They just came fresh from the NAM, won a prize, and they have posters today. So please talk to them about the AMT and about their work. And I'm just going to say cool things are afoot. We're going to connect the black hole to the jet, lots of other sources. And I'll skip over that and say space is great. We're going to do it. X-rays in space. I'll leave it at that. Okay, thank you.